Hi, everybody. Sorry I had issues this morning, but it seems to be working okay at the moment, so we can get started. So today we're going to be talking about the chemistry of ions. It's going to be a little different from the chemistry we looked at before, which is covalent compounds, covalent bonds that we express with the line either in between the symbols or just the lines, as we saw in the line structures a couple weeks ago. So this time we're going to look at ions, which is kind of the rest of the periodic table. So if I pull up a periodic table here. There it is. We focused mostly on here carbon, nitrogen, oxygen, and hydrogen. And today we're going to kind of look more at the rest of it and how do we deal with those types of compounds, many of which are considered ionic compounds. So to review from the thing that you did about atomic structure a while ago, atoms have protons, neutrons, and electrons. The protons have the positive charge, neutrons have neutral or no charge, and the electrons have a negative charge. So the balance of the protons and electrons is going to determine the overall charge, the electrical charge on that particle. So we can say proton and neutron, or sorry, not neutron, electron. That's what's going to determine the overall charge on a particle. Sorry, this thing is drawing really slowly right now. Hopefully it'll be okay. So let's take an example. Let's look at sodium. Now, if we just write Na, and we're talking about a single sodium atom, we can figure out the numbers of protons and electrons the way you did a couple weeks ago by looking at the periodic table and the atomic number. So let's do that. All right, so we see sodium over that way, number 11. And that means that it's going to have 11 protons, right? Because the atomic number always tells us the number of protons. And then if it's a neutral atom, if it has 11 positively charged protons, then it must also have 11 negatively charged electrons, so that the overall charge is 0, and there's nothing written in this upper right-hand corner. Now, if instead we were looking at a sodium ion, sodium has a +1 charge as an ion, and we'll talk about how you figure that out in a minute. But just looking at the particles right now, that means that it's going to have still 11 protons, because if it had more protons, if we made it positive by adding a proton, then we'd be turning it into a different element. We have 12 protons, we don't have sodium anymore. Instead, we have magnesium. See number 12, magnesium over there? All right. So in order for it to have an overall +1 charge, that means that we have one fewer electron. So in becoming an ion, sodium has lost an electron. It has one fewer electron than it did before. All right, let's look at another example. A chlorine atom versus a chlorine ion, or a chloride ion. And again, we'll talk about where those things come from in a second. Right now, we're just focused on the particles. But by the end today, you should know how to determine what that charge is going to be for several of the elements. So again, we look at the periodic table. We find chlorine, which is right here, and it's got an atomic number of 17, and that means it's going to have 17 protons. And we might as well just write that here as well, right? We always have 17 protons. Anything that is Cl, that has a symbol of Cl, is a chlorine atom, means it has 17 protons. Now, the neutral atom will have 17 protons as well, but the negatively charged atom will have an extra electron. So it'll have 18 electrons instead of 17 because it's now negatively charged. It has a -1 charge. All right. So what can we do with these things? Well, of course, we could keep looking at other atoms. We could have +2, +3 ions, -2, -3, stuff like that. But what I'm most interested about in today, and what I want you to be able to do today, is what happens when these things come together and make ionic compounds? Ions don't exist just on their own. You can't just get a bottle of chloride ions or a bottle of sodium ions. They always need to be paired plus and minus with other ions. So an ionic compound is always going to have two parts. It's going to have a cation, which is the positively charged part, and it's going to have, use a different color here. It's going to have the anion, which has the negative charge. So let's say we want to make a compound between sodium and chloride. We look at the sodium cation of plus, the positively charged sodium cation, the negatively charged chloride anion, and we put them together to make a compound. Now here's the thing. When you put them together to make a compound, the compound needs to be neutral. All right, so overall 0 charge. Now for sodium chloride, that's pretty simple because we can just, we got +1, -1, those balance each other out. So our sodium chloride compound is going to look like this, NaCl. When we put them together, notice we don't write the charges anymore. The charges are for when the ions are by themselves to distinguish an atom from an ion. But once they're together, we know it's an ionic compound, and so we don't need to have those there anymore. Okay, so let's back up for a second and talk about how we figure out, actually, that sodium is positively charged and chloride is negatively charged. Well, there's sort of an easy and a hard answer to that. We're going to focus on the easy one at this point. When we talk more about electronic structure of atoms, it'll give you some more background information on that. But for now, we can look at the periodic table and we can just say that certain areas of the periodic table always have predictable charges. So if you see the little numbers up overhead, and if you can't read them on this, depending on your screen size, you can pull up a periodic table anywhere, and they should have these numbers on the tops of the columns. The official correct numbering is just 1 through 18, but there are some older numbering systems, those are the other ones that are shown, that can also be helpful. So 1A, 2A, 3A, 4A, 5A, and so on. This whole middle section is this B section. We're going to deal with that later. None of those elements have a predictable charge, which means we can't just look at the periodic table and figure out what those charges are going to be. So we're going to ignore them for right now. But the other parts of the periodic table, we can guess. So let me... Oh no, let me go back to the notes here. There we go. And I'm just going to draw kind of the shape of the periodic table. And we're going to make that middle part really skinny because, like I said, we can kind of ignore it here. So here's this middle section, this B section. Just kind of not think about that right now. And instead, we're going to focus on these first two columns. So here's 1 and 2, 3, 4, 5, 6, 7, and 8. That would actually be 13, 14, 15, 16, 17, and 18 with the normal numbering. And so the ones where we can predict the charge and we know that it's generally going to have the same charge, all of the elements in column 1, when they make ions, make a +1 charge. And the elements in group 2 make cations with a +2 charge. Then it gets a little trickier. So 13, we just have one element really with a really predictable charge here that we're going to worry about, which is aluminum, 3+. Then we're not going to think about 14, 15 for now. The ones in 16 are generally going to make a -2 charge. The ones in 17 are generally going to make, whoops, not a -3, a -1. And then in 18, there's 0. So no ions in 18. So if you have an element in those columns, you can guess And actually, this first little part of 15 also makes a -3. We can say that. So if you're talking about an element in one of these columns, you can guess what its charge is going to be just by its position because of this predictability, these known charges. So we're going to use that information to help us to name some, or I'm sorry, draw some formulas for some names. So let's say we did sodium chloride. Let's say we want to do magnesium fluoride. All right, so here's a ionic compound, magnesium fluoride. What's the formula for it? All right, so here's how we're going to figure that out. First, we're going to look up these elements in the periodic table, and that's going to tell us what their symbol is and what the charge is if they're in the right spot, if they're in those spots where we can predict the charge. So back to the periodic table. I see magnesium over there, number 12, next to sodium. And I see fluorine right at the top here, above chlorine at number 9. So magnesium is going to be Mg, fluorine is going to be F. And then the other thing we can tell from this is the charges. Magnesium is going to be +2 because it's in that column number 2. And fluorine is going to be -1 because we said all the elements in this column are -1. So let's write that down. Now that we know that information, I'm going to keep the same color coding of blue for cations and red for anions. Now, when you have a charge that's greater than 1, +1, +2, -2, something like that, there's a couple ways you could write that. The most common is to put the number first. It's the least confusing, but it's also correct to write +2 instead of 2+, and that's fine as well. Okay, so we've got our two elements. We know the charges. So the last thing to do is to put them together in a neutral compound. Now we can't just make this MgF. And the reason for that is that magnesium is +2, fluoride is -1. So a compound that's just 1-to-1 ratio of magnesium to fluoride is always going to have extra positive charge. We can't have that. They need to be the same amount of there needs to be the same amount of positive and negative charge in the compound. So to do that, what we're going to do is add a second fluoride ion. So if these combine in the ratio of 1-to-2, 1 magnesium to 2 fluorides, now we have a neutral compound. And in the physical compound of magnesium fluoride, this is exactly what we see. We see a ratio of 1 magnesium for every 2 fluorides. And the way we express that in a formula is with a subscript. MgF2. And this is what's really different from the organic molecules that we saw over the last few weeks. When we looked at molecular formulas of those molecules, the subscripts told us exactly how many atoms are in the molecule. So if it said C4H10, that means a molecule with 4 carbons and 10 hydrogens. But in ionic compounds, those subscripts don't tell us the exact number of atoms because we don't have a discrete molecule. We have this kind of more just massive extended structure. So all this is telling us then is the ratio. It's saying that for every magnesium atom, there's going to be 2 fluoride, magnesium ion, there's going to be 2 fluoride ions. So we have the ratio as the formula instead of an exact count of the numbers. All right, so that's pretty much it in terms of how to put those formulas together. Now we're going to encounter a couple other situations where it can get somewhat tricky. So let's look at aluminum oxide. And depending on where you're from, you may also think of this as aluminium. That's another correct name for that. Aluminum oxide. We'll pull up our periodic table again. And I can see aluminum right here, number 13. And that's in that one weird spot where we know it's a +3, but it doesn't really, not in a column where they all have to be +3, but aluminum is +3. And then oxygen is right over here. So oxide, even though those names are a little different, it is true that the anion names often change and have "ide" at the end. And so oxide here is going to be -2. So we can write those down. Aluminum 3+ or +3, and oxide 2 minus or minus 2. All right, so now we need to combine them into a compound. And this is where it can get a little bit tricky because we've got a 3 plus and a 2 minus. Whoops, and I forgot the L in aluminum, Al. We can't just add an extra oxygen because then we'd have 3 plus and 4 minus. That still doesn't balance. We need the same total number of positive and negative charges. So the only way to do that is to find a common multiple of both. And that turns out to be 6, so 6 plus and 6 minus. And we get that when we have 2 aluminums and 3 oxygens or oxides. So you don't always just vary one of the components. You sometimes have to vary the numbers of both of them. And so our final compound here should be Al2O3. And that's the formula of aluminum oxide. All right. So another thing that comes up sometimes is, what about that middle area of the periodic table? We just sort of ignored it, but those are real elements and they all make ions, and we do have to deal with them. So the reason we ignored it before, if I pull this up here, is that all of these elements in here, sorry, I can't reach that far, my camera cuts out, including these kind of in orange also down here, orange and green, we left those out because they can make multiple different charges. So instead of saying, oh, this is always +1 or always +2, an element like iron, Fe number 26, sometimes is +2, sometimes is +3. Some of these other elements can have even more different charges than that. So that makes it a little bit trickier because we can't just look at the periodic table and say, oh, it's here, it's this charge. So we need another technique. And the other technique is that when we see a name with one of those elements in it, it's actually going to tell us the charge. So if we want to know a compound, we can't just say iron oxide because that's not enough information. We don't know what the charge on iron is if we just say iron oxide. What we have to do is actually specify the charge, and that's done with Roman numerals. So iron 3 oxide, that 3 is the charge, not the subscript, the charge. And that's a really common mistake. Everybody wants that 3. Everybody wants iron 3 oxide to mean iron, little 3, oxygen. That's not how it works. It's the charge. Iron 3 is the charge. So that tells us that the ion that we're dealing with here is Fe3+. And oxide is always the same. That's always O2-. So now when we put this together, our compound, just like with the aluminum one above, is going to be Fe2O3. All right, so we still do the same kind of balancing, but we just have to get our cation charge from the parentheses. And they're always positive. So all of those elements that you'll see in there will always be positive. All right, let me check the chat, see if I have any questions here. All right. Okay, the last category of ions that we're going to deal with are called polyatomic ions. Polyatomic ions are ions that have more than one atom. And so these are things, some of which we've seen already, are things like hydroxide, which is OH -1. So in this case, this ion is made up of 2 elements, O and H, but it's not like oxide and hydride or something like that. It's just hydroxide altogether. It's one thing, and it's got a -1 charge. And there's a bunch of these. I'm not going to list them all or even many of them, just a few. There's nitrate, which is a common one, which is NO3 -1. There is sulfate. SO4, 2 minus. There's a whole bunch. There's even some positive ones. Oh, I should have made these in red, I guess. There's ammonium. Which is NH4 plus. So several different polyatomic ions. When we make compounds with these, the tricky part is it's just something that has to be memorized. And you, in this class, don't have to memorize them. But in general, if you wanted to know how to make these compounds, you would have to either memorize them or look them up. Because there's no kind of simple just shortcut to say, oh yeah, you just look at the periodic table or something. It doesn't work like that. So let's say we had we wanted to write a formula for, we'll stick with our magnesium sulfate. Actually, let's do nitrate so I can show you one other thing. All right, magnesium nitrate. So the magnesium part is easy. We've done that now. That's on the periodic table. We look it up. We find that it's Mg2 plus. Now nitrate is a little different. We can't look that up on the periodic table. How would we even know not to look that up on the periodic table? Well, one key is it ends in 8. Any of these ions that don't end in ide, I-D-E, are probably polyatomic ions. Are certainly polyatomic ions. There are also a few that end in "ide" just to make it extra confusing, but there's just a couple. So most of them are going to end in "ate" or "ite" or something like that. And that's your clue that you're not just dealing with a single atom from the periodic table, you're dealing with a polyatomic ion that you have to look up and find the formula and the charge for. So we do that. Let's say we look this up and we find that it is NO3 and it has a -1 charge. Once we have that information, we can do the same thing that we did with all our other ones. We can just balance the formula. So we can notice that magnesium is +2 and nitrate is -1. So we can get a second one in there. And then the way we write this formula when we're dealing with these polyatomic ions, just to avoid confusion, is we use parentheses around the ion. So MgNO3 2. And that's what the final formula should look like for magnesium nitrate. All right, so that's kind of an intro. There's some good references linked on Blackboard for how to get some more practice with this. This is one of the objectives for this module, so make sure you feel comfortable doing this kind of thing that we just went through today. You don't have to memorize any of this stuff, but you do have to know how to look it up and how to figure out those formulas and what those names mean. Also, I should note, you don't have to go the other direction. You don't have to name the compounds, like come up with the correct names from the compounds. We didn't really go through all those rules. But if you see the name of a compound, you should be able to write the formula. That's the goal here. All right, well, I will see you on Wednesday for the biodiesel analysis. And then next Thursday, we'll talk about macronutrient structures and the biodiesel reactions. So have a great weekend. Hope this all goes okay for you, and I'll see you next week.